Okay. So the title, I tried something to be inspired by Avi, a few nouns and commas as connectives. We'll see about it later. So I want to start with thanks, and I want to thank the organizers, which in a moment will be problematic, but I really want to thank the organizers for organizing such a thing. It's always taken for granted, and I think it shouldn't be taken for granted. So where are the organizers? We already. Ran also is taking a dip. The problem is I'm really sympathetic to the organizers because organizers usually only hear complaints and in some cases even curses. Actually, I want to join those who curse because I think the worst thing on earth is to talk after Ronen. And really, I don't know how to conduct myself now. Okay, so another thank is also to the PC chair, which is not on this conference, but on another conference, which also usually hears complaints and curses, especially from people whose papers were not accepted, like my papers, which were not even submitted. Right, and still, it's not an excuse. But I think we should somehow, Russell wants to say something?
Are you upset about not winning the lottery just because you didn't play?
I didn't hear exactly, so I'll let everybody enjoy. Where were we? This was, I'm totally off because of Ronen. Originally, I was thinking that the organizers will probably want me to tell stories about Avi. And that's a small dilemma because really Avi doesn't like to hear me telling stories about him. But I think that really we have bigger depths to the organizers than to Avi even. And therefore, I want to tell only one story. So I think that's a story that Avi hates the least. And also, I'll tell it in a nicer way than usual. Because it's his birthday, so I have to be nice to him. It happened many, many years ago in MIT in the mid-80s. And, okay, right. So Avi was visiting MIT for a week, and then one day I come to the office. It was around 11:30. You'll see why the time is important in a moment. And Avi asked me if I can bring him to the airport, and how long will it take me to bring him to the airport. So I told him it will take me about 15 minutes. He said, well, my flight is at 4, but I want to be at the airport at 2. So let's just go ahead safely. Okay, so in 11:40 already felt that it is not safe enough. So he asked me, how long will it take to go to the airport? So I told him it will take 15 minutes and we can continue. So 11:45, same question, same answer. 11:50, at some point it cannot be contained anymore. At around 12:10, I give up and I drive him to the airport. And indeed, in 12:30 we get to the airport, and then there is a final exchange in which Avi confessed that he was lying. Flight is actually at 7 o'clock. Now let me be nice. We have all to appreciate Avi. So he had really a tough week. So it's a week in which he was hosted by Silvio and Shafi. And let me demonstrate to you their idea of time. So once Silvio, so some time, unspecified time, because time is not to be specified, otherwise the story is not universal and generic or whatever. So in some cafe in the Mediterranean, we need not specify beyond. So the following exchange goes on, also 11:30. I meet Silvio and ask at what time is his flight today. He says, in the afternoon. Okay, so 11:30 is not on the afternoon, so I wait until 1 o'clock, and I ask him again, at what time is the flight? Say afternoon, and then at 2 I ask again, what are you bugging me, you know, the flight is in the afternoon. He says, but when? So I insist that he takes out the ticket. However, inspired by Silvio, we made it in less time because Silvio has control on time, and we got to the airport on time and everything like that. So now about Shafi, she has to get somewhere. Since time is also a continuous thing and a quantum thing, so there are many options of getting to the other place. So there are many flights, so she just books all the flights. And then at some point, which is less than 2 hours before the last flight, she realized that the last slide. Okay, so let's go to the airport. Yeah, but first we have to take the slides, and then we have to have dinner, and then we have to go to her house and fetch her clothes, and then we get to the airport on time. So Avi was somewhat nervous that I picked up also with such habits. So I had to be on the safe side. Okay, so back to the talk. I want somehow to abuse or use the occasion in order to promote some direction of work which Avi and myself started a few years ago. It wasn't very noticed, and I would like to make it slightly more noticed, so I'm picking this occasion in order to do it. The buzzwords are in the title, and we'll go through them, so I don't expect you to get anything from the title. It was a joke. The title, not getting. So we are going to talk about constant depth circuits, and Johan is sitting here. Yeah, he's to blame for the first line. So parity in depth D requires circuits of such depths. We all know this result. It is tight. Johan says, it's nice to have tight results because then you know that you get it right. However, supposedly we understand what is going on, but we don't really, because that's parity and that's not the largest possible size you can have. So there are two famous, actually there is one famous barrier or one famous frontier, which is to get lower bounds for more powerful circuits than just AC0 circuits. So say AC0 with parity or with threshold or with slightly. But another frontier which is less explored, I think, which is I find even more annoying, is that this lower bound of this sub-exponential lower bound is not the best you can hope for, and you could best hope for an exponential lower bound. And actually, a counting argument tells you immediately that you need exponential size, you know, even regardless of depth. So why can we not prove such things? Or why don't we want to do some progress on proving such things? And I would like to go into it in the talk. So there will be 3 suggestions, and then there will be some meat to it, maybe, and we'll try to go. Okay, so the first suggestion says the following. We know that parity is hard. What will be a nice candidate to prove strong? And parity is not only hard. The result of Johan, as I said, by his middle name, it's optimal. So you cannot have a larger size. But other functions can have larger size, as we said. So what other functions do we want to try? And the suggestion is to try multilinear functions, because Madhu likes them. By this I mean that there is a function on 2 blocks of variables. Each block is of length n, And the function is just taking an arbitrary collection of monomials with one variable from each block. So this will be a multilinear function or a T-multilinear function. It's associated with a tensor which says T-dimensional tensor which says which monomials are in the expression and which are not. So basically this is what we want to compute. We want to compute such a function. I want to say that the tensor has to be non-trivial because, of course, if the tensor, for example, is a subcube, then it reduces to parity. And if the tensor is very sparse, it also reduces to parity. So these are two things you don't want to do. But other than that, world is as open as we want. But we will want also the tensor to be explicit. But even before saying that, it's not even clear, and that's a good sanity check, whether we can show that there exists, forget about explicitness, whether really multilinear functions requires the size that we are shooting for. And this is the size that we are shooting for. And the question is, does there exist any, for t equals 1, Johan was able to prove it, but we want to do it for t equals 2 or for other t's. And actually, throughout the talk, think of t as small. A constant will be happy enough for us. You can go to log n. If you go to log n, you see what happens. It will be exponential, and this is the aim that we are going for. But we are very far from there, so we are starting with this. So that's the first suggestion. The second suggestion is that things are complicated enough and bad enough already in depth 3. So let's talk only at depth 3 and forget about anything else. At depth 3, what Johan says is, again, that parity requires exponential square root of n, and any result which will talk about more than exponential than square root of n, okay, don't cheat me with putting a log factor or stupidities like that. I mean, significantly better than exponential in square root of n, we will consider it interesting. And we want to go in this direction. So that's the second suggestion. So the goal, again, is to show that, and if we are really bold, we want the function to be explicit. We want an explicit function that require such depth circuits of such size. And what will be coming in the next slide is another sanity check, which will say that we are not able to tackle this goal yet, or now, or in our lifetime, maybe if we are pessimistic. So let's consider a restricted model of depth 3 circuits, which I would claim is a very natural one, and let's just try to prove lower bounds on it. So this will be the next slide. So the next slide, I'm not tight here. Okay. Is there a board? No, it's hidden, so I cannot write on a board. No, it's okay. I'll not write. So it will be less clear, but then it's not my fault. So it's the board fault and things. So what is the restricted class of functions that I'm talking about, that I suggest to talk about? So the motivation is, how do you know that Johan is tight? So if you think of parity, and Johan says that parity requires exponential, we're talking all the time of depth 3. Parity requires exponential is square root of n size circuits. How do we know that this is tight? How do we construct a circuit of this size? So you all saw it, but I want to show it and you all saw it also in this case, but maybe not so explicitly. So let me just draw it slightly more explicitly. What we know is the following thing. What we do in order to compute the parity of n variables is to take one parity gate which has a branch in or a arity of square root of n, feed it by square root of n parity gates, which each of them takes square root of n other variables. So these variables are not written here, and just look at it as a circuit, it's an arithmetic circuit now, or it's a circuit over GF2 doing also parity gates, but small ones. The crucial thing is that I'm using parity in order to do parity, but I'm using parity with small arity in order to do parity with large arity. So, so I have this trivial circuit in the arithmetic world. I translate it to the Boolean world, and I call this translation canonical. And what does this canonical translation does? It takes every Boolean, every big parity gate. In this case, I want to think of this parity gate as a multilinear, generic multilinear gate, and I don't really care what it is. It happens to be parity of square root of n things, but what I care is that it is a function of square root n things, and I just implement it in the most straightforward way possible, say by DNF and CNF formulas. So I implement the top one by CNF and the bottom ones by DNF so that I can claim that 2 plus 2 equals 3 and not 4, but that's all to it. And this should inspire the general model of canonical circuits. So in general, what I'm saying is the following. The model in one incarnation, now is the simplest incarnation of the model, says the following. You have a circuit, an arithmetic circuit of depth 2 with general multilinear gates. Each gate is allowed to be a multilinear gate. The only restriction is on the arity of the gate and on the number of gates. Actually, the number of gates is, I don't need to talk about it because it's depth 2, so the arity of this gate determines how many gates there are. But let me just, for sake of clarity, say that I'm bounding two parameters, the arity of the gate and the number of gates. And I want to say that whenever I have such a circuit, I immediately get a circuit of this form which has size that is exponential in the maximum between the number of gates and the arity of the gates. So, and that's trivial because what I used when I implemented Johan, you can use also here. So each gate is a parity, is a multilinear gate with a arity entries. You can implement it by a CNF of size 2 to the a, and you just need to combine these circuits together, and this is what you get, and you'll get a canonical circuit. So, is there water somewhere? Ah, sorry. It's well hidden. Thanks. So organizers are gift of nature. If I had the board, I could show you a more so the more general definition is on the board, but the proof is not on the board and on the slide, and I needed the board in order to do it, but I will not do it. So more generally, I want to say that I could have an arithmetic circuit with these general gates of arbitrary depths. Doesn't need to be depths 2. And I'm saying that if I have such a circuit which has gates of arity alpha, and it has m such gates, then it will yield a depth 3 Boolean circuit of size which is exponential both in m and in alpha. And the trick, if you don't see it, is just the following. You have on the top gate, you will have an implementation of a non-deterministic gate, supposedly. So you're going to guess all possibilities for the outputs of the m gates. That's why it will be exponential in m. So you have m gates, you guess, which means you branch exponentially in m to all possibilities of assignments to the m gates. And for each one, you do verification of the thing, and if you look at the details, it works. So basically, it says that whenever you have an arbitrary circuit of this type, which is, I will call the complexity A-n complexity. A is for arity, n is for numbers. So whenever you have a multilinear circuit with arbitrary depths, with arbitrary multilinear gates, you will get a Boolean circuit of size which is exponential in these parameters. So the offshot of this is that now what I want to do is I want to study canonical circuits, which are circuits which you get in this transformation. In other words, I can just study the original multilinear circuits, because the complexity of the two creatures is the same, just one is exponential of the other. So basically, what I want to study is really the complexity of the AN complexity of multilinear functions. So that's basically the goal. And now we can get to the question whether canonical Boolean circuits are as powerful as general circuits. And my answer is that I believe so. And Avi's answer is that he doesn't know and he refuses to cast a vote. And now we have to go to Ronen and to ask what do you do in such a case when these two teachers disagree.
He's more afraid of you.
No, I think he's more... Okay. So once I win. But I think that it is not so important to fight out this dispute because I think in any case the following is true. So on the one hand, assuming at all that the first suggestion is okay, that really multilinear functions require a bigger Boolean size than parity, assuming this is the case, then if we are ever going to prove lower bounds of that type, we have first to prove, not first, but we will be proving also lower bounds on these canonical circuits. So since this is so difficult, why don't we start with these canonical circuits? So that's the first thing. And the second thing that I want to tell you is that really, existentially, I totally understand what is happening with these canonical circuits. It's just that I don't understand what is happening explicitly. But we'll see it in a moment. Okay, so what did I mean by this claim? So I meant the following two theorems. Let me click also on the other one. So the first theorem is an upper bound. It says that any T-linear function has complexity of the right form, of the form that I was shooting for. So it's T to the n to the T over T or plus 1, or whatever the expression is. So this is the case. And actually, you can easily show it even by using only depth 2 circuits. I'm talking now about these arithmetic circuits. So there exist easy, I'll show you in a minute, constructions of depth 2 circuits which have this complexity for any function you pick, for any T-linear function you pick. The second thing is the more important one, which I was alluding to, is that a counting argument can show you that actually for every T, almost all functions have this complexity. So what we are shooting for is something which should be reachable, essentially, unless you believe that things exist which cannot be demonstrated explicitly. But basically what I'm saying, almost all functions have high complexity, and please let's prove, let's find explicit functions and prove high complexity on them. High is, now we are not in the exponential scale anymore, so we are talking about the exponent, or we are talking about the AN complexity. So interesting will be anything which is above square root of n. So square root of n is a parity, is a complexity of parity. Anything above square root of n is interesting. And the third result, actually I forgot to say at the beginning, all this talk is based on two works, one with Avi and the second one with Avishai, which is sitting here, and I don't have a picture of him, but we have it in flesh, so we don't need a picture. So the third result is that actually you can do this. That's the first step. I think there are many steps to go, but the first step is that we know, and I can show you, explicit 3 linear and 4 linear functions. Why do I show both? Because for one, I know a result which is better than the other. For the 3 linear, I know to overcome U1, square root of n. Instead, I have n to the 0.6. And for the 4 linear, we have n to the 2/3 almost, as close as you want to 2/3. And notice by theorem 1, if this result was for 2 linear, then this is the best possible. But we're talking about 4 linear, so it's not the best possible. But still, it's progress. Okay, so this is the goal. It's a good point to ask how am I doing on time. Another 15 minutes. Okay. So I think I'm just fine also. Okay. So first I want to show you sketches of these 2 easy theorems. So what I want to show is the upper bound and lower bound. Upper bound for every function and lower bound for almost all functions. And the upper bound will just, again, I don't have a board, but the upper bound will just say the following. Take the dem tensor, let M be the complexity that we want to reach, okay? The tensor is this t-dimensional object. Just cut it into M pieces evenly. So we have to have something is, yeah, no, I think is, yeah, what is written on the board is fine, and I will not talk, I'll let you read, because whenever I try to read the mathematical expressions, I mess up. So basically, what we do, it's a trade-off. The bigger the cube is, the bigger arity you have. On the other hand, the bigger the cube is, the less cubes you have. We want to have an equal number of cubes versus their arity. And there is this trade-off when you do the calculation, it's just what is written there. So basically, this is totally generic. Any function you want to do, you partition it into cubes. Each cube, when you are in a cube, it means that there is a gate which can compute exactly this cube with complexity, which is t times the side of the cube, just straightforwardly. That's the hardwire of the gate is computing this cube. So this has this complexity, and we're done with theorem 1. Theorem 2, as I said, is just a counting argument. You count how many possible multilinear gates you have. Here I'm capitalizing, till this point I didn't capitalize on the fact that the gates are really computing multilinear functions. But at this point I have to capitalize on this, otherwise the counting will not work. And basically we're done. So that's the proofs of theorem 1 and 2. The proof of theorem 3 is more complicated. I have to show you explicit functions which are doing these things. So basically it boils down to 3 lemmas. And it goes into what is called rigidity, which was also on the title of the slide at the very beginning. Could have been ignored until now, but lemma 3.1 and the other lemmas refer to it. The first lemma says that if a function has a low an complexity, then it cannot have high rigidity. So if it has an complexity m, then the corresponding, and I'm sorry, I forgot to say, yeah, okay, let me back up. I'm going to prove the theorem by using results on bilinear functions. So it's not clear for a moment why do we have 3 linear and 4 linear functions in the theorem, but we'll see in a moment when we get to the second and third lemma. So the first lemma says the following, that if a bilinear function has an complexity m, then the corresponding matrix doesn't have rigidity m squared for rank m. So what it means is basically that you worry too much. So this means that basically we'll have a definition of rigidity in the next slide, so let's not worry about it for the time being. Just notice that I hid something SS, which will mean superstructured, but don't refer to it for a moment. So the lemma says not only that it doesn't have such rigidity, it doesn't have even so basically, we'll go to the next slide, we'll see it. Not only is that, okay, we'll need the definition, so we'll get it to the next slide. So basically, I'm saying something. It's a word, doesn't matter what it means. I'm saying it has two versions. One is the simple one, and second one is a calibrated one, which I will use in the third lemma. So the second lemma says the following, that a random Toeplitz matrix has rigidity at least n.1.8 in the exponent for rank n06. So that's a rigidity result. It's not in the range that interests most people who are talking about rigidity, but it is a result in which the rigidity parameter times the rank parameter is significantly bigger than n squared. This is not known, and it is a big problem or a big question in the other parameters. But in the parameters, it was also not known in this. Yeah? In the next slide. Right now, it's just a generic name, doesn't matter what it means. But what I'm saying is that lemma 3.1 already says that we are above the obvious in that parameter, which was undefined and will be defined next slide. And
the more rigidity is, the bigger this parameter, the harder it is to find such matrices. And it's random. It's also random. It's not explicit.
Right. That's a great point. But let me just go back to the previous question. Like Gil was saying, but was not saying, a random matrix, a random n by n matrix has rigidity n squared for rank n, or more or less like that. The problem is getting an explicit matrix. You want an explicit matrix in which the product of these two parameters is significantly bigger than n squared, and this was not known for us, for the interesting setting of parameters, but it is now known for the setting of parameters which is important for our project. Noga's result says the following. In lemma 3.2, I'm talking about a random Toeplitz matrix. It's not a random matrix, so it's a random Toeplitz matrix. So the point that I'm stressing is that the randomness complexity which is involved here is linear in n, whereas in a total random matrix, the randomness complexity is n squared. And by a prophecy, which happens to be correct in this case, you can translate results which are semi-explicit, let's say, with randomness complexity n to explicit results. We'll see it in a moment happening. But this translation is by introducing auxiliary variables, and these auxiliary variables will make the function 3 linear rather than 2 linear. So that's the big picture. The third lemma says it's an explicit construction, but Avi would say something which I also say, but it's in Hebrew and it cannot be translated, so yeah. It's explicit, but it is really, you don't want to see it. So it's explicit, but not natural. So a Toeplitz matrix is natural, but and the function that I'll show you is natural. But this is saying that there is some distribution on matrices, which, like in the previous one, takes only linear complexity, and it happens to be implementable by bilinear functions, and that's the condition that the prophecy wants. And therefore, I can take this bilinear thing combined to the other bilinear thing and claim that 2 plus 2 is 4, and by which I get this 4 linear function. But everything will be hopefully more clear in the next slide. Okay. So the next slide has the definitions of rigidity and of super rigidity structure. Let's erase it for a moment. No, how do I go? No. Okay, that's enough for one slide. So focus on the definition. So actually I'm not defining rigidity, I'm defining what is not rigidity. So when a function doesn't have some level of rigidity. It doesn't have a rigidity S for rank R if you can write it or decompose it as two matrices. One is very sparse, it's called S for sparseness. So a matrix has is S sparse. It means that it has only S once. In the lemma 3.1 or in the lemma 3.2, you see that I'm talking about rigidity n to the 1.8. So I'm talking about a matrix which has a size, has n square entries, of which only n to the 1.8 are ones. The rest are zeros. It's a very sparse matrix. And the other matrix, so of course, I'm not talking about sparse matrices. This will be useless. I'm talking about sparse plus rank. So a matrix is rigid, or is not rigid, if it can be expressed as a linear combination of a sparse matrix and a matrix of low rank. So if the sparseness is S and the rank is R, I say that it does not have rigidity S for rank R. Now let's go back to slide to lemma 3.1. It says that if a bilinear function has low an complexity, which is what we are talking about all the time, so if it has, say, an complexity n to the 0.6, then I'm saying the corresponding matrix does not have rigidity m cubed for rank m. So it doesn't have rigidity n to the 1.8 for rank n to the 0.6. Who cares? Who cares numbers, right? But the end result will be that if I combine lemma 2 and lemma 1, I get that there exists an explicit function, or I get that a random toplet matrix, which is a bilinear function, has an rigidity n to the 0.6. So from all these numbers, we got a result. So the result is that a random toplet matrix has complexity n to the 0.6, while parity, we remember all the time, has complexity square root of n. So we are significantly above parity in this complexity measure. Right. We'll come to it. So right now, it's not kosher. It's a semi-random matrix. It's a random tuplet matrix, which means it's a matrix which is defined by n to the 1.8 by 2n entries, which I cannot draw, but you know, the diagonals. So I'm not sure whether it's written on this slide or I forgot the slides already. It is written, sorry. Okay, so we are fine. No, what did I do? Sorry again. Okay, so the answer to all these questions is hidden in the third line of the box. So what I'm doing here, it's not written. I don't know why it got erased. Okay, so I have to write it somewhere. What I'm saying is I know that there exists a random matrix M such that this function, how do I point? Such that this function, the function which is written on the third line, has high rigidity. So right now it's non-explicit, right? But no, but there is no board. I want to write on the board.
You want to write on the board?
I want lots of things, but nothing is happening. מה יש? דדל.
Okay.
Here. So what I cannot do with this stick is replace this matrix Mij. This is a toplet matrix, non-explicit one. Now what I want you to do is to think of it that it is defined by two n variables. So the entry mij is a variable with index I minus j. So now introduce an auxiliary variable which ranges over 2m values, which has 2m, it's actually a block which is bigger, but it doesn't really matter. So introduce this auxiliary variable, call it z, and write here, rather than mij, write z in index I minus j, and write z also here. So we have a three linear function, which is a function of x, y, and z, and the value of it at x, y, and z is what is written here. Except that you replace mij by xi minus j. Z I minus j. So that's all that there is to it. So basically, the reasoning is now the following, and that's standard. But the non-standard point, which I wanted to emphasize, is that the cost of this replacement, the cost of replacing randomness, which annoyed Noga, and I think it was Shai. The cost of getting rid of the randomness was merely introducing one additional block of variables. And this has to do with the linearity of the particular construction. It's not a generic claim. But what is generic follows now. What is generic is saying the following. Look, it cannot be that this three linear function can be computed by small complexity. Because if it could have been computed by small complexity, by just fixing the values of the variable z to what they are in the non-explicit mi, in the random one, and you don't need a random one, it's enough that there exists a hard Toplitz's matrix, you will get a circuit which violates the assumptions about the non-explicit or semi-explicit or semi-random or whatever Toplitz's matrix. So that's the reasoning here. And we get better results. So far, we proved only a lower bound of n to the 0.6, and this was for a three linear function. Now, if I want to get a result for which is slightly bigger, then I'm applying this one. But here, I have a new term, which is this superstructure. So it's not the standard definition of rigidity, which half of you saw sometimes else, but it's a new definition of rigidity, a more restricted one, meaning that it is easier, hopefully, to show such matrices. So the definition goes the following. Firstly, you say that M doesn't have structured rigidity if it can be decomposed the same way as it was composed before, but with an additional condition. And the additional condition is that the sparse matrix has a specific form. It's a sum of S matrices, which each one of them is a rectangle by S of S by S. Or the ones of it sit inside such a thing. So that's a structure rigidity. And the curse, which is superstructure rigidity, let's not even go into it. But what is interesting about it is the following, that actually it is equivalent to AN complexity. So this definition actually is equivalent. So at some point, you can say that we don't gain anything by going to rigidity, because at the end we use this definition. But it is useful to think about things this way, I would say. So basically, if I'm trying to wrap up, I'm going back to this lemma. I'm saying that not only that a matrix with low complexity doesn't have this rigidity, but it even doesn't have this superstructured rigidity. So and therefore, to prove that some function doesn't have superstructure rigidity is good enough. But that's already, we're getting technical, and I want to go on. So this was another attempt to define these terms, and I think I want to wrap up. It's probably a good time, right? So basically, what I would like to keep in mind is the definition of AN complexity. So the entire model, it's a model, a restricted model of proving lower bounds on depth 3, which goes to the arithmetic world. So it's actually a model in the arithmetic world, if you want to think about it like that. We have this theorem, which says that we have explicit 3 linear and 4 linear functions which have non-trivial complexity, which is getting high, but not high enough to my taste. So the goal is really to have for every t, in particular for t equals 2, we didn't get it. We only got for t equals 3. So for every t, to get explicit functions which have this complexity. Remember, we know that such functions exist. They exist in abundance. We just don't have an explicit one. And one specific open problem which could be of some use to getting practice or to making progress is just to show an explicit 2 linear function, not 3 linear functions. 3 linear function we have, to show an explicit 2 linear function with complexity which is significantly bigger than square root of n. And the more interesting open problem would be to show an explicit O of 1 linear function which has a complexity which is almost linear. It's the first step, just go beyond n to the 2/3. Because n to the 2/3 I know. And probably because you will have to go to higher dimensions, we are not 2 linear anymore, so probably we'll have to give up on the rigidity approach, and you will have to find a new approach. But maybe not. Maybe you can generalize rigidity to higher dimension. We tried, and we were not able to do it successfully. And Avishai doesn't believe, so. No. You say that we didn't succeed. This even I know. And also back to the original sanity check, which I also don't know, and I also find interesting, to just show that there exist functions, forget about explicitness, to show that there exist multilinear functions which have high complexity in the normal Boolean world, not restricted. Okay.